Okay, and so last time we started talking about, and today we're really going to focus on time-dependent perturbation theory. And so this is focused on the question of how do states evolve in time when we have a Hamiltonian that has some possibly complicated time dependence. So we're assuming that we're going to be given a Hamiltonian, which is an easy Hamiltonian that has no time dependence and the time dependent part, and that we know somehow or another what the eigenstates and eigenvalues are. So maybe it's the harmonic oscillator and we just happen to know them. Maybe it's something else and we have to solve them using perturbation, time-independent perturbation theory. But we're just assuming that we know the eigenstates and the eigenvalues. And then the next thing we did is we defined transition amplitudes. For which there are different notations in different books. And my notation for transition amplitudes is a little a, and then we have an initial state to a final state, and then we put the final time and the initial time. And it's just defined to be this matrix element, where we use the interaction picture unitary operator sandwiched in between the initial and final states. So as a recipe for computing this, we have the following things. The hard part is the UI operator. In fact, that's the part that you can't really do exactly. But you can do a Dyson series expansion for it. And so the first term in the Dyson series is it's the identity. And the next term, which is the one you almost always end up using, is this. It's an integral over all times in between the initial time and the final time of the interaction period version of the perturbation Hamiltonian. That's just the first term though, then there are many more terms. So this is the Dyson series. And then I have to tell you what W sub I is. So reminder, that is equal to the unitary operator for time evolution taking only the H0 Hamiltonian, sandwiched on either side of the Schrodinger picture interaction Hamiltonian. Okay, so when we did all of this, we derived this using the interaction picture. But now that we've done that, we don't have to talk about the interaction picture anymore if we don't want to, because notice the structure of this is everything here is in the Schrodinger picture because it has no I subscript. That allows us to construct W sub I. Then we plug it into the Dyson series. And so now we've got U sub I in terms of Schrodinger picture operators, namely this one. And then we plug it in here. And so once we've done this, everything's in the Schrodinger picture. And in fact, if you look at some books, they don't ever mention the interaction picture when they're deriving this stuff. They sort of derive it without that language, but it amounts to the same thing. Okay, so now that we've got that, then we note that the time dependence of states and when I say this, I mean Schrodinger picture. The thing that we've been used to is the following. The state at some time is equal to a sum over eigenstates of H0, which I'm calling M for the moment, some coefficient that depends on time times M. So far I haven't really done anything because I know that any state can be written as a superposition of eigenstates of H0 because H0 is an observable, and therefore there's a theorem, well, there's a definition actually that says an observable is something that you can expand any state in terms of. Okay, but now I need to tell you what the coefficients are. The coefficients C are given in terms of the transition amplitudes. So you sum over the transition amplitudes multiplied by a phase factor. Okay, and the phase factor is curly En minus curly Em over H bar. That's determined in terms of the H0 eigenvalues. Then I have my transition amplitude that comes in. And then the final ingredient here is the initial condition for the coefficient. So Cn T0. So presumably, if you're given a problem to solve, you're given the initial state, hopefully. And so those are initial conditions. Then you want the transition amplitudes, and then this thing you know because you know everything there is to know about H0. So one note is last time I was in a bit of a hurry towards the end, and I messed up and I wrote this equation wrong. I don't know why I won't highlight. There we go. I wrote that equation wrong, which just goes to show that you should never believe anything I say in lecture. Your default should be to believe the notes, and you also shouldn't ever believe the notes because I do make occasional mistakes in the notes. Okay, so anyway, those are the coefficients, and so some notes on this that we were getting to last time is, first of all, the transition amplitude, if I evaluate it at time t0, so really I'm asking what's the transition amplitude from t0 to t0, and since I'm not waiting any time, that means nothing happens. So that's just this matrix element because I'm plugging in phase factors that are all 1. And so that's the Kronecker delta of Mn. And so what that's telling you is that if you plug into this equation, okay, that's just going to say you end up in the same state you started. This factor is 1. And so as you would hope, the coefficients at time t0 are equal to the coefficients at time t0. That's what the equation's telling you, which you know is true. Okay, and then there's a special case, which is a favorite of problems, and that is you assume that you started off in an H0 eigenstate. So if only one of the initial coefficients is non-zero, and by the way, if only one of them is non-zero, then hopefully it means if you normalized things properly, it's not only non-zero, but it's actually equal to 1. Okay, then the probability to start in that state N and end up in a different eigenstate M is just the square of the transition amplitude. Okay, so this is probability to start in state N at time t0 and to end up with, or really to find yourself in the state M at time t. Okay, so we worked all this out with the interaction picture, and now perturbation theory just consists of making a single assumption. Time-dependent perturbation theory means you assume that W is not big. And we'll have to be more precise about what we mean by not big a little bit later. Okay, but we're assuming W of t is small. And so again, what small means, we'll probably have to evaluate on a case-by-case basis. But we're doing it using the Dyson series. And so more specifically, let's go back up to this equation. The Dyson series means the hard part is the UI operator, and we're going to truncate that at some number of powers of W. And the number of powers of W is, in almost all cases, either 1, which is the most common case, or 2. If it's 2, it's probably going to be a hard problem. So, okay, so if you do that and you evaluate the transition amplitude, you can divide it up into parts depending on how many powers of W there are in it. So there's a part 0, which has no powers of W, and a part 1, which has 1 power of W, and a part 2 that has 2 powers of W. Okay, so number of powers of W. Okay, and so the 0th order one is really easy to evaluate, because that's just going to be the matrix element Mn, oops, which is the Kronecker delta of delta Nm. So that's saying, really that's saying if I turn off my W, then if I start in an eigenstate of energy, I end up in the same eigenstate of energy. Okay, now things get more interesting if we go to the first order. And so when you plug in the term in the Dyson series that has 1 W in it into the expression we had above, we get minus I over h bar. There's an integral to do, t0 to t dt1. And then there's this. There's the matrix element of the final state, a phase factor that comes from time evolution in the interaction picture. That's where it came from. Then there's the Schrodinger picture interaction Hamiltonian, W. Then there's the opposite phase factor here. But they don't count, they don't cancel because H0 may not commute with W. In fact, it almost certainly doesn't. Okay, and now the point is, if we look at the H0s, both of them are adjacent to one of their eigenstates. This H0 is adjacent to that M. This H0 is adjacent to that N. And so we can evaluate them on their eigenstates and turn them into numbers. So let's do that. That means we can write the final answer as at first order in perturbation theory, like this. So I'm just rewriting the integral, but now I pull out those H0 operators and I find that what I get is the exponential of t1 minus t0 times a number that we'll call omega mn times this matrix element. Okay, and so that's true where the numbers omega mn are equal to curly em minus curly en over h bar. So omega n mn is a frequency because it's an energy divided by h bar. And we know from, for example, the harmonic oscillator that energies are h bar times angular frequencies. Okay, and so basically all we have to do in first order time dependent perturbation theory, similar to first order time independent perturbation theory, is we have to evaluate the matrix element of the perturbation, and unlike first order perturbation theory, it's not an expectation value. Here it's really a matrix element. because we're asking for transitions from one state to another. And then we have to weight it by a phase factor. And then when we've done that, we have to integrate over it. Okay, so that's first order perturbation theory. And so let me just write this down. First order perturbation theory. This really applies if n is not equal to m. Okay, and then if so, the probability for n to transition to m is the square of the first order transition amplitude. So when I've written that, of course, I've used the fact that n is not equal to m so that I didn't have to include the A0 part, because the A0 part I see from up here is going to be 0 when n and m are different. So that's how I can get away with that. But I can't always get away with that, because to be valid, this better not be too big. Okay, because the reason for that is just that probabilities are not allowed to be bigger than 1. That's just a basic fact. And so we must have that this thing is less than 1. So if you compute it and it didn't come out less than 1, then it doesn't mean you made a mistake. It just means that the approximation we're making, where we only work to first order in perturbation theory, unfortunately is not valid. And then you can try maybe going to second order in perturbation theory. But if you think about it, you might just be in big trouble, because if the first term is too large, then that just means W wasn't so small. And then there's no reason to expect this thing is necessarily going to converge. Not only that, but even if it is less than 1, you still might be in trouble. So this is a necessary condition for convergence, but it's not sufficient for convergence. And the reason for that is just that it might be true, and sometimes it even is true, that the first term comes out okay, it's not too big. But then when you compute the second term, you find out it is really way too big, and then the series that you're doing won't converge. Okay, so that's one thing that we have to worry about. Another thing that we have to worry about in first order perturbation theory is that for n equals m, didn't mean to say not equals, for n equals m, it's not valid ever. So why is that, and what do we mean by that? So let's just compute the first order transition amplitude for a state to go to itself. So let's write that down. This is minus I over h bar. I have the integral to do. Okay, but now let's go back up to here. And so now we are plugging in m and n are the same state, which means from here, this factor is 0, which means this whole factor is 1. So I don't have to write that. And so all I have is this part. Okay, so let's write that down. This is m w of t1 n. And now the thing is, what do we know about that matrix element? We know it's a real number because W is a Hermitian matrix. Oops, I forgot one important thing. This M is also N. Okay, so now we're computing the diagonal element of a Hermitian matrix, which is real, always. And then we're integrating that, which doesn't change the fact that it's real, because now we don't have that phase factor. And then we've got the minus I sitting in front. So that means the whole thing is a purely imaginary number. which isn't by itself a bad fact. There's nothing wrong with that. But now the probability for n to go to n is at first order in perturbation theory. Now we can't forget about the A0 term because it's not 0 anymore. Okay, and so let's evaluate this. This is 1, is the first one, plus I times something. And then we're taking that times its complex conjugate. And so that result is equal to 1 plus the something squared. Remember, something is a real number. And so that's greater than 1. So this always fails because probabilities can't be greater than 1. And so the resolution of this apparent problem is that you cannot just truncate things at first order in perturbation theory if you're trying to calculate the probability for a state to remain the same state. Okay, so for the problem of n equals m, you need at least second order in perturbation theory. So I'll say at least. And so when we write probability for n to stay as the state n, we should write 1. That's really my A0 n goes to n term, plus A1 n goes to n, which we know is a pure imaginary number, plus now we're going to include A2 n goes to n, and then square the whole thing to get the second order in perturbation theory. Okay, so let's multiply that out. We get a term that's 1. We also get a term that's A1 n goes to n squared, just like we did before. But now what we're including is the cross term when we do the square between this and that. So that's 1 plus this added to 1 plus this complex conjugate. And so that is plus 2 times the real part of A2 n goes to n. Okay, and then there are more terms. For example, there's the cross term when I do the square between this and that. But that will be third order in perturbation theory because this will have 1 W in it and this will have 2 W's in it. And so the product of them will have 3 W's in it. And so if we're just working to second order in perturbation theory, we are done. So I'll write here plus third order. Okay, so we also, fortunately though, we know one other way to calculate this probability. In fact, the other way is what we should have done originally maybe, because it's easier. Okay, and so we know the probability for n to go to the state n is 1 minus the probability to do anything else. So this is 1 minus the sum over all possible m's that aren't n of the probability for n to go to m. Right? It's got to do something. It's got to end up in some state. And so if it didn't end up in n, then the sum of all those things has to equal 1 minus the sum of all those things has to equal the probability that it stayed in the state n. Okay, and now if we evaluate that to second order in perturbation theory, that's 1 minus, for m not equal to n, there was nothing wrong with just saying this. It's the first order transition amplitude. Okay, and now we have two different expressions for the same quantity. The probability of n goes to n. So we can take this and set it equal to that and see what happens. And one good thing that will happen is the ones will cancel out. Oops. The ones will cancel out. And then we can take this with the minus sign and move it to the other side of the equation where it will combine with that. And so the net of doing all these things is a very nice formula that if you take the sum over all m's, whether or not m equals n, of the first order transition amplitude complex squared, that's going to be minus 2 times the real part of the second order amplitude to stay in the same state. Okay, so that's a general formula, and it's actually, if you need to do second order in perturbation theory, this is a useful check on problems like that. Okay, any questions so far on what we've done with first order perturbation theory? All right. So now let's think about the actual computation of second order perturbation theory. So when we wrote this down, we were really arguing very indirectly. We were figuring out what this real part of this had to be just based on things like probabilities have to sum up to 1. But now we can go back to the definition of a n goes to m, that transition amplitude. And we're just going to take the Dyson series and we isolate the one term in it that has 2 w's in it. And that gives us a n goes to m at second order, the second order part. Okay, and if you stare at that Dyson series enough, you'll realize it has the following parts. There are 2 powers of minus I over h bar squared. There are 2 integrals to do. 1 over d2, and then the second integral has upper limit of integration d2, and you're integrating over d1. And then you have a big matrix element that we're not probably going to be able to fit on one line, which is m e to the I t2 minus t0, h0 over h bar. My w evaluated at time t2. Remember, w depends on time, so it matters when we evaluate it. Then we have another factor of e to the I t1 minus t2, h0 over h bar. Then, as promised, we have to continue on the next line. There's another factor of w, this time evaluated at time t1, another exponential factor. And then finally, we get to write down the ket for the initial state. Okay, so now we have to evaluate this thing somehow. And the strategy for evaluating it, as usual when you don't know any other way to proceed, is to use completeness. And so we are going to write down that the identity operator is a sum over H0 eigenstates, which I'm going to label as K1. And so we write ket K1, bra K1. We're using completeness of, so K1 equals H0 eigenstates. And so I'm going to use that, but where am I going to put it? So it turns out a good place to put this identity, to insert this, is right in here. So why would we do that? What's the reason for this strategy? This is very often why we use completeness. We're doing this so that if you then stare at the resulting expression, every H0 in it is adjacent to one of its eigenstates. So an eigenstate, bra or ket, one or the other. Okay, and that means we can always replace them by whatever is the energy eigenvalue for that adjacent bra or ket, curly EM, curly EK, or curly EN, as the case may be. So as the case may be means, for example, for these H0s, they're adjacent to that M. For these H0s in this exponential, they're going to be adjacent to the K1. And for these H0s, they're adjacent to this N. And so in all cases, we can replace them by their eigenvalue because they just act on that Brouwer ket to give that number. Okay, and that's why we wanted to put it here, because otherwise these H0s would have been all by themselves and they wouldn't have had an eigenstate on which to act to turn themselves into numbers. Okay, so now we can replace them by numbers, and so that really solves the issue of how to evaluate this thing. So I'm just going to rewrite it. Really, okay, this depends on t and t0. That's a comma. Okay, and so as before, we have minus I over h bar, two factors of that. We still have our integrals to do. Okay, now we have to remember that we're summing over all the K1s. But now we have omegas, just like we did at first order in perturbation theory. So those are our phase factors. Okay, and then we have a matrix element M W2 N. Sorry, not N, K1. Okay, then we have another phase factor, and really I could put this phase factor wherever I want. It's a number now, it's not an operator. So this is K1N, but I'm leaving it there because that's where it started. So it's just a useful mnemonic. And then we have K1, W of T1, M. Okay, and so what have we done? We've boiled this thing down to, can we evaluate matrix elements? So even though W might be complicated, we know what these states are. And so if we can evaluate the matrix elements, then those become numbers. These are numbers that we know. They depend on the T's, but then we have to integrate over the T's. But in principle, this can be done. Okay, so now let's say we wanted to go to third order in perturbation theory, which I promise you I will never make you do. But it's useful to know how you would do it, just in case, in some future project that you're doing, you need third order in perturbation theory. And also useful just to understand what the structure is of the way this goes. So if I'm doing the third order contribution for n goes to m, there are going to be 3 powers of minus I over h bar. And there are going to be 3 integrals over time. The first one I'm going to call dt3. Then I integrate with upper limit of integration t3 over t2. Then I integrate with upper limit of integration t2 over t1. Okay, and now I'm going to do Now I have all the e to the I h0 things, and for each one of them, I'm going to put in a complete set of states. So now I'm going to do a sum over two complete set of states, K1 and K2. By the way, that explains why I called it K1 and not just K before. It's because in the general case, there will be K1, K2. If I did fourth order in perturbation theory, there would be K3. Okay, and then I have a bunch of phase factors. So e to the I T3 minus T0 omega MK2 matrix element MWT3 K2. Another phase factor here, T2 minus T0 omega K2 K1. Another matrix element, K2 WT2 K1. Another phase factor, e to the I T1 minus T0 omega K1N. And finally, the last matrix element, K1 WT1 N. Okay, and so all of this stuff comes from the Dyson series. And so then if you stare at the Dyson series long enough, you'll realize that there's actually a diagrammatic way of writing this. So there's a diagrammatic version where instead of writing down all those complicated factors, we're just going to draw lines and dots with the understanding that each line and dot means something in the equation. Okay, so let me do it the following way. I'm going to draw a double line with an arrow on it. And that's going to represent the full transition amplitude. To go from T to T0 to T. So I'm going to label the first part of the line as T0 and the second line as T. And I'm going to say I'm in the state N here, and I end up in the state M here. Okay, and then this is going to be a sum of terms that correspond to orders in perturbation theory. So the first term, I'm just going to draw a single line, T0 at N, T at M. And this diagram represents zeroth order in perturbation theory, which is just the Kronecker delta, delta NM. Okay, and then if I do first order in perturbation theory, I'm going to do this. I'm going to draw a diagram. But now I'm going to put a dot in the middle, and the dot represents the time that I'm supposed to integrate over. So I'm going to label this as T1. Okay, and that's going to represent a superscript 1. And then at second order in perturbation theory, I ended up integrating over 2 times. So I'm going to label this one as T1, this one as T2. The beginning time is T0 still. This is N. This is M at time T. Okay, and I just put arrows just to remind myself that I'm going forward in time. And then this arrow in the middle has a label that we're going to call K1. Right? And then I'll give in a moment, I'll give the general rule for translating these diagrams into numbers. But the third order in perturbation theory that we wrote down is going to have 3 dots on this line. This initial is still T0 and N. The final is still T and M. This is going to be time T1, T2, T3. This is going to be state K1, state K2. Okay, and then a general contribution is just gotten by drawing a diagram, which is a line with a bunch of dots on it. Okay, and then here's the rule that you can figure out or show gives the correct formula for every time you have a dot with a line coming in and a line coming out, which is labeled, so let me put K and K prime here. The K and the K prime could be N or M or K1 or K2 or anything. And I label the dot by some time T sub j. Whenever I see that in the diagram, I write down the following factor, minus I over h bar. I write down an exponential phase. Okay, and so that exponential phase depends on the time Tj. It depends on the difference in energies between the states K prime and K. And it comes with this matrix element factor. Okay. Whenever I see that, I also know that I must integrate over those times. So integrate over, and the integrals always start at t0 and end up at tj plus 1 if I'm integrating over tj. Okay, and then the last thing we have to remember to do is we put in the k's because we were using completeness. And so we must sum over all k sub j's in the diagram. Okay, and so if you write those rules down somewhere and include them in these diagrams, then the diagrams, which are pretty easy to construct because they're just lines with dots on them, that gives you what the various orders in perturbation theory are. As I said, you will not need to know, for sure, you will not need to know third order in perturbation theory for any problem that we do in this class. Okay, any questions on that before we do an example? All right, so let's do an example, and we'll do another example next time. So this example is we're going to do a one-dimensional harmonic oscillator, okay, which carries a charge. And then we're going to put it in an electric field. Okay, and we're going to start in the ground state to make things easy. In a general problem, we wouldn't necessarily start in the ground state, but we'll start in the ground state in the far past at time t0 equals minus infinity. Okay, and so here's our unperturbed Hamiltonian. It's just our old friend, the harmonic oscillator. And now I'm going to tell you the perturbation to apply. Okay, and the perturbation Hamiltonian, I'm going to choose to be the charge with a minus sign times an electric field, which we're going to take to be the following. It's some value E0 t squared over tau squared times x. So if I take the derivative of that, I get the electric field. And so E0 is an electric field. And the meaning of the exponential factor there is it's 0 at positive infinity and negative infinity. And so I'm starting with no field. I turn it on and then I turn it off again. Okay, and so this peaks at t equals 0. So here's the problem. At late times, after the perturbation has turned off again, so that's going to be t equals positive infinity. What's the probability that we find ourselves in some other state that we didn't start in, like not the ground state? So what's the probability of being in an excited state n. Okay, so to do that, we need to calculate the transition amplitude. And we're going to do that in first order in perturbation theory. So we're going to say, what's the probability of starting in the ground state, ending up in the state n at t equals plus infinity, given the initial state at minus infinity. So we trust our formulas, which say this should be minus I over h bar, integral from minus infinity to infinity, because those are the relevant times now, dt1, matrix element. N is really our final state that we were calling m before. And there's minus q e0. Okay, I put in my perturbation Hamiltonian, which depends on time. X is the position operator, 0. And then I can't forget my exponential phase factor, which is e to the I h bar omega n over h bar. So let's just concentrate on where did that come from. Okay, that came from the fact that my final state energy is h bar omega n plus 1/2. And my initial state was the ground state, h bar omega times 1/2. And so I take the difference between those, divide by h bar, and that gives the exponential. Oops, and I forgot a factor of t prime there. So let's rewrite that just to make things nicer. This is going to be IQ over h bar times E0, integral from minus infinity to infinity, dt1. Oops, I used t1 and t prime interchangeably. Let me call it t prime, I guess. Okay, and so now there's, I'm going to plug in for what x is in terms of creation and annihilation operators. So there's going to be a square root h bar over 2 m omega, n a dagger plus a, 0. And then I have my time-dependent parts. That's rewriting the mess above it. Okay, and now we know from our study of the harmonic oscillator that this matrix element is very simple. Okay, this is nothing other than the Kronecker delta of n and 1, because the A acts on the ground state and gives nothing. The A dagger acts on the ground state and gives the state 1. And so the matrix element's only non-zero if that n is also 1. All right, and so we can rewrite this as I Q E0 over, clearing out the h bars, square root of 2 m h bar omega, delta n1. In this example, the matrix element was really nice. And then finally, we have to do this integral. So it's the exponential of minus t prime squared over tau squared plus I omega t prime. Omega is the omega for the oscillator. Okay, and if you compute that integral, that turns out to be square root of pi times our time constant tau. Tau is really controlling how fast we turn on and off the electric field, times an exponential of minus omega squared tau squared over 4. Okay, so we've successfully computed the transition amplitude. And now to get the probability, we just have to square it. Okay, and so that's q squared E0 squared pi tau squared over 2 m h bar omega, just squaring everything above. And then there's a factor of e to the minus omega squared tau squared over 2, because we squared it. Okay, so we've calculated the probability. We turn on and off this electric field. It jostles this harmonic oscillator. And this is telling us what's the probability that we end up in any other state. The answer is it can only end up in the state 1 above. That's a feature of first order perturbation theory. So that's the approximation. And it's proportional to how long we wait, or how long we turned it on for, and it's proportional to how strong the electric field was. Okay, but this approximation fails if it's too big. Okay, so if too big. So if we compute this number and it comes out to be a small number like 0.01 or something, then we can trust it, or at least maybe we can trust it. But if it comes out to be 3.9, then we know it's bogus, because no probability can be 3.9. Okay, and so built into the answer, the numerical answer, is whether or not you should trust it. It just can't happen that it's bigger than 1. And so if you do find it bigger than 1, then you know that you need to go, you either can't do perturbation theory at all, or you have to go to next order in perturbation theory. Okay, so we're out of time for today, and so we'll do another example next time. But next time is not Friday, as I understand it, because according to the academic calendar, it's a administrative holiday, which I was never told whether or not that meant we didn't have classes if we're doing remotely, but in any case, we also have PhD exams for at least some of you. And so there will be no class on Friday, and therefore I will see you on Monday.
Thanks, Dr. Martin, appreciate you.
Thank you so much.
All right, good luck on your other exam, and talk to you later.
You too, thank you.